I want to make this little recording to help with the spreadsheet problem. We did a lot of this in class, and I went ahead and put the heading titles up here to start to speed things up. For the time, we want to do in 0.1 increments. So if we'll put 0 and 0.1 here, we can block those with the mouse, and then grab this little corner and copy it down. And it will just go ahead and increment by 0.1, because that's going to be our time step. The initial velocity was 0. V2 is going to be 500 miles per hour. And to convert that into meters per second, we'll multiply by 1609 and divide by 3600. And I have left out the equal sign. You always have to put equal if you want to put any operations in there. The thrust, we've got rho pi r squared over 2 multiplied by v2 squared minus v1 squared. So we'll do the equal. For the density of air, we got 1.2. And then for pi, we use pi. And then that's the Excel for pi. Pi, open close parenthesis, times the radius of this propeller is 1.5 meters, and we got to square it. Times, and then we got to take v2 squared and minus v1 squared. And divide by 2. So I've got the 1.2 pi r squared over 2 multiplied by v2 squared minus v1 squared. And I've got it set up so it'll index. As I copy it down, it'll go to the new v2 and v1 values. The arrow drag is 2.2 times v1 squared, so we'll do equal 2.2 times v1 squared. And then the net force acting on the airplane is the thrust minus the drag. So we got the thrust minus the drag. Once we have the net force acting on the plane, the acceleration of any object will be the net force divided by the mass. So we'll take the net force and we'll divide by the mass, which is 6,000 kilograms in this case. And as I said in class, I just wasn't thinking right. I've chosen either too low of a mass or too much thrust. And there's no way, we probably wouldn't have an airplane that had 3.5 G's acceleration on takeoff. But as far as numerically, this will work out fine. We've just chosen a little bit too high a numbers. So if this is the acceleration, we're going to assume it's constant over the time step. So in dynamics, we have that the velocity is equal to the initial velocity plus the acceleration times time. That's v is v naught plus at. So over here for this one, we'll do equals, and this is the initial velocity for that time step, plus, and this is the acceleration, times. Now we could just use 0.1 seconds because our time step is always going to be 0.1, but if you had irregular time steps, you would take this one minus this one, and that would give you the time step, as we go from this line in the code to the next line in the code. And so by doing that, we find that at the end of 0.1 seconds, it's going 3.5 meters per second. V2 stays constant. That's what we're supposed to assume for the problem. The thrust force depends on V2 and V1. And so by indexing it down here, my mouse will cooperate. We get to this. You notice it's a little bit smaller because now we have a V1 to subtract off. The arrow drag started at 0, but now we have a velocity of the airplane, so we've got about 27 newtons drag. The net force, of course, the the thrust force went down, the drag force went up, so the net force ended up going down. And then we can go ahead and compute the acceleration. And now we've got everything all set up. So we can index it all. We can just block all of these and we can copy them down. And when we've done that, it gives us, the speed at each time increment. Of course, V2 stays the same. And the thrust force, just decreases as we accelerate forward. The drag force increases and the net force decreases. And so the acceleration decreases gradually as we step through the process. But you notice the acceleration isn't changing very much. So that assumption, that approximation we're making that the acceleration is constant over that time step is a pretty good approximation. The airplane is supposed to take off when we get to 160 miles an hour. So we might, in miles per hour, we might want to get the speed. And we know that, V1 is the speed of the airplane, but that's in meters per second. So I could take V1 and multiply by 3,600 and divide by 1609, just the reverse of what we did to convert miles per hour into meters per second. Get that set up, and then we can copy it on down. And so that's our speed as we go down the runway in miles per hour. We know that when we get to 160 miles an hour, the airplane's going to take off. So, I could try some intermediate time steps and work it here, but for simplification, I'm going to assume it takes off here. At 164 miles an hour. Now, I think I want a few more time steps so that I can plot this out. So I'll go ahead and do this, and by blocking 2 like that, I can get it to go ahead and increment for me, and then I can just block all of these and copy them down a little more. And right at this point here, when we go into the net force here in column F, right now is the thrust minus the drag, but now we're going to start climbing. We're going uphill on a 10% grade. So we're going to have the 10% of the weight of the airplane is going to act against us as we climb upward because it's a 10% grade. So the weight of the airplane is 6,000 kilograms times 9.81. And so that would give us the weight of the airplane, and then times 0.1, because we're not going straight up. We're just going on a 10% grade. And so that subtracts off then gravity. And so at that point, we'll modify it. And at that point, we start subtracting off the gravity loading because we're climbing. And we'll go ahead and copy that on down. And as we do, that impacts everything. You notice the spreadsheet is updating itself. Then for altitude, the plane is now climbing at a 10% grade. So we can come in and we can do altitude. And we'll do that in meters. And we start at 0 because all the time it's going along the runway, it's at 0 altitude. So I'll just copy 0 on down to there. And then at this point, it takes off. And it's climbing at a 10% grade. So I've got the speed in meters per second over here in column B. And distance is velocity times time. So we'll take the speed here. And if you want to, we could do the average speed. We could average over that time increment, and I'll go ahead and do that. So for average speed, we could take this one plus this one, and we would be dividing time by 2 times the time increment, which is this one minus this one. So that gives me velocity times time, but I need to divide by 2 so that then see I've got this, I'm averaging the velocity by taking b26 plus b25 over 2 and then multiplying by the time increment. And so that would give me the altitude, and that would be in meters. And once we have that, oh, I left something off though, that just gives me the change in altitude. I've also got to add the initial altitude, which of course is 0 for the first step. But then after that, we need to add it on. So as we copy that down, then we can get, how the altitude is going to increase with the airplane. We could go ahead and copy the speed down if you wanted to too. And that's in miles per hour. Then the next thing we want to do is to draw some graphs. I think I'm going to show you how to do altitude. So we're going to insert, and here we're going to want to put in a chart. So it puts it in just blank, and then we'll right click on the chart, and we want to select the data. This comes up, we want to add, we're going to add a line to the chart. We really just need the X and Y values. So we'll do time on the X value. We'll come in and we'll go ahead and then you'll click that. And then for the Y values, we'll do this altitude column. And click here. And you see how it's going to appear. This is our altitude, and the first part it's running along the runway, and then it takes off at a 10% grade as it starts climbing up to its cruising altitude. And then we can click OK and OK. Now we probably want to title this something, and we click on the chart title and block it, and we'll say altitude versus time. That sounds like as good a title as any. We can come over to this quick chart element, add chart element. We probably want to put axes titles, and so we can come over and click on primary horizontal, and it puts one in there for us. And axes titles and primary vertical, put one in there for us. For the vertical one, that would be the altitude in meters. And then for the X one, this is time in seconds. And there you have it. It's a pretty good chart. You could plot just about anything using this same. You can, add another, insert another chart and just do whatever you want.